Hello and welcome. So in this series, we will start with an idea of what neural networks are and why anyone might be interested in implementing or understanding them. Neural networks are generally used in supervised learning. In supervised learning, we have training data and their corresponding labels. So let's see an example. If we have a training data consisting of images of cats and dogs, so the corresponding images are labeled. So, like uh, dogs have label 0 and cats have labels 1. So this is what is supervised learning. So neural networks, also known as artificial neural networks, are inspired by our brain, which consists of millions of neurons connected to each other, passing information throughout different parts of our body. So this is our neuron, which is present inside our brain. The information is passed from one end of the neuron to the other end, passing information throughout our body using these neurons. So So similarly, we have neural networks or deep neural networks, which basically consists of more than one hidden layer. This we will talk about hidden layers later. So let's now talk about neural networks and how they work. But before that, let's see some applications of neural networks. So these are the some of the most state-of-the-art applications of neural networks. On the left side, we have a convolutional neural network, which is used in our object detection task. Use YOLO v5 architecture for object detection. As you can see, it can detect multiple objects within an image. On the right side, we have OpenAI GPT-2 model, which is a language model which is capable of producing human-like language. So this was just two of the state-of-the-art applications of what neural networks can do. So next step is to understand what a simple neural network is and how does the information passes from one end to the other end. Okay. So right now we have three inputs, x1, x2, and x3, and we have a hidden layer and an output layer, which consists of a class. Consider it as 0 and 1. Okay. So to explain it, let's just forget about this hidden layer. Okay. So I'll draw a simple example consisting of only one output neuron. Okay. So just forget about this for right now. Suppose we have three inputs, x1, x2, and x3, and also each connection is allotted with a weight value, which is a trainable parameter that later determines how much to consider this input value or how relevant this connection is. Each connection has a weight value. Okay, so I'll just draw it here for you. So this only determines how much x1 is to be considered in this output and how much w is to be considered for x2 and similarly for w3. Now, in order to pass this information forward to our first hidden layer, that is which is consisting only of one neuron, summation of the product of weights and inputs takes place. This is known as forward propagation because we are going in forward direction. Okay, so I'll just explain it in a minute. What does z does? Okay, this function is basically summation of x into the weights, okay, plus a bias value. I will explain in a minute what does bias do. Okay, so the main function of this neuron, it has two functions, all right. One is the summation of the product of weights and inputs plus a bias, and then we apply an activation function. Okay, this is the summation value, and then is the activation function. So our z becomes z is equal to x1 into w1 plus x2 into w2 plus x3 into w3. Okay, plus a bias value. Now each neuron has its unique bias value, all right. Suppose we had another neuron here and neuron here. The summation will take place. Okay, the same. It will have different weight values. All right. Sorry, this and this. It will have fully connected, and each neuron will have a different bias value. Okay. Just consider this. This is the formula of the output of one neuron, and then we apply some activation. So this gives us the output of the neuron. So to summarize, each neuron has two functions. All right. One, summation of inputs and weights. Second is to plus the bias value. Yes. Second is to apply activation function. So the formula becomes z is equal to summation of inputs into weights plus bias. This is the main formula of a single neuron. Now let's talk about weights and biases. If we plot a graph and if we analyze our equation, that is z is equal to inputs into weights plus bias, this actually you guys will actually recognize this equation as y is equal to mx plus b. Okay, so we can draw it as a straight line passing through the origin. Sorry, just consider it as passing through origin. This is our z value. Okay, now z is w into x plus b. Now if we increase our weight value to +1, then the slope will get steeper. It will go towards the y-axis, right? So just remember this: whenever we increase the weight value, the slope gets steeper. Okay, so the weights determines the slope. On the other hand, if we increase the bias, okay, let's say bias is equal to +1, then the graph, this line will be on this point. All right, where this is a gap of 1. So the purpose of bias is to offset the output positively or negatively, which helps us to change overall function. It is also a trainable parameter. Okay, just remember that w and b both are trainable parameter. That means during the training process, like during the calculation of z and backpropagation, these parameters will learn. Okay, that means the values of weights and biases will keep on changing and improving itself. So this was all about weights and biases. Now, before coding an actual neuron, I will briefly explain about a function that we will apply to our final neuron output, that is a step function. Okay, so a step function looks like this, because this is what step looks like. Okay, its definition is so if our output value, that is the z value, what was the z value? For example, we had 3 inputs, right, and 1 neuron. So suppose this is x1, x2, and x3. So this gives us the output z, which is equal to y. We consider it as y, so which was the summation of the products of weights and inputs, right? Summation of weights into inputs plus a bias. This was our z, all right. So if this value is greater than 0, then the output will be 1. Else, if it is less than or equal to 0, it will be considered as 0. Okay. So this is what our step function does. So by this, it means that if the neuron's output value is greater than 0, which is calculated by this formula, is 1, that is the neuron fires. Okay. And if the output value is 0, then the neuron doesn't fire. That is, the output is 0. Okay. Now this is what is known as an activation function, which basically determines whether the current neuron will fire or not. We don't generally use this step function as our activation function anymore. We use many more advanced activation functions like sigmoid, tanh, ReLU activation function, which we will cover in depth in later videos. So let's continue with the implementation of a single neuron. Okay, so let's assume we have 3 inputs values and 3 weights values, all right. So inputs is equal to, just take any values. I'm taking random values. Let's define our weights. Let it be 0.40, 0.98, and 0.15. Okay, these are just random values. Now, as I explained you earlier, this will be a formula. Okay, summation of weights into the current weight value into the current input value. Okay, and also we forgot the bias. Let's say 2. Okay, now we will calculate our output as not out. I messed up. Okay, output will be weights 0 into inputs of 0 plus weights of 1 into inputs of 1 plus weights of 2 into inputs of 2 plus bias. Okay. So So this is our output of one single neuron. Okay, this Z. Cool. Now we can print output. Okay, so now if we run it, Python b1.py, so this is what we get as our output of one neuron. Okay, 3.18. Cool. So we can also round this by putting inside the round function, but that's not necessary right now. I just wanted to explain the basic thing behind what a neuron does. So this is the output of one neuron. Okay, so this is exactly what we are doing in this code. Cool. So this was all for this video, and I hope you enjoyed it. In the next part, we will come up with the implementing multiple neurons. Okay, so see you in the next video.